Okay. All right, guys. So we are recording. All right, so we're recording. We're going to get started class today. All right. Yeah. So let's get started. So today's the last lecture, right? And I'll have a little bit of time towards the end of class today. If there's a few people that haven't presented still, you'll be able to present today, but that will be towards the very end. Okay, so I just have a few last topics that I want to cover. So we're going to wrap up the material. Remember, you're working on your term project, right? So, and I'll basically conclude stable diffusion discussion today. If you remember, we were kind of stuck at the loss function, so I'm going to go over that today, and we should be able to finish that. Are there any questions before I begin? All right, so so the topics today, so we'll be wrapping up stable diffusion, right? Going over the final ideas of it. And we're also going to cover the cross entropy, which was one of the loss functions that we were going to finish up with. So let's go ahead and take a look at bright space. So next week, I'll remind you, is term project presentation. So everyone needs to present it with their groups, the work of your stable diffusion model. Okay. So I'm going to go ahead to the table of contents. Let's click on table of contents here, which you should be seeing. And then I'm going to scroll down. So the last topics that we're covering are, as you can see, stable diffusion, cross entropy. I provided a few links here. And here you can take a look at this code, and it'll show you some information on how to load images from a folder and be able to load them into a tensor. Okay, so, but I leave that to you. You might use that for your stable diffusion project. All right, the last topic that we will cover today, as I said, is cross entropy, which is this new module I added, and the notebook is there. And then today we're just going to continue with our discussion of stable diffusion, basically to wrap it up. All right, so I'm going to go to the GitHub, and I'm going to go to latent diffusion here, which you remember this is where we were. And basically you're reading all these blog posts, etc., all this information. Okay, so I'm going to, so if you notice, I added some notes, okay, and some graphs, and we're going to cover this today, the basic idea of the stable diffusion model. I also added some additional Jupyter notebooks. This one, loss small, is one basically that we're going to cover today, and it just goes over how the loss function works and what is the objective to train a stable diffusion model. It's actually pretty simple, but I'll discuss the many hours that I spent trying to reverse engineer this function, and at the end of the day, I think it's actually very straightforward. So yeah, so the loss small basically is our discussion on how the loss function works for stable diffusion. So in the past, if you remember, we've done MSE or cross entropy, right? So those are the two loss functions available. Okay. Small stable diffusion, we covered this one last week, if you remember, and I just printed some images, right? And we were looking at an image and how it's being perturbed, basically, which is basically the idea of adding noise. Okay, so that we've covered. Stable diffusion MNIST, this is the code that I provided to you, okay, initially. And I added this one called Streamline Stable Diffusion. So basically, this is like everything that you need for the conditional MNIST. So I took out, things that are not needed and just kept it, as the word implies, streamlined. So basically that's the one that you should be using for your project. If you find a data set with some classes, use this, you're good. But obviously I want you to take it further, right? Take it as this is a term project. Does that make sense, guys? Streamline would be the one actually to use for your project. So it should be just, with other images. Obviously, remember the two things that I want you to do is the images need to be in color now. And the other thing is, the conditional part, right? So are you going to take it to the point of words even, right? So it's up to you. So I'm not, or are you you can keep it as classes, but just, use. So it's up to you, basically. But anyway, so I played around with these notebooks. As I said, I am, very clear of how Stable Diffusion works right now, but I was a little bit confused by that loss function, but we're going to discuss it today and, give you some insights into how it should work. So these are some of the notes from the previous time. I basically updated this notebook. So the README. So basically Stable Diffusion, we're doing MNIST. The UNet I have not changed, so it's the same details. The only thing I will say about the UNet is that we're using a UNet that uses, so there's two versions of the UNet. One that, if you remember, right, so the way that the UNet worked is that it would downsample and then upsample, right? And from one layer in the downsampling, we would concatenate it to the corresponding layer in the upsampling. Instead of upsampling, what you can also do is you can add, right? So there's these two approaches. The adding is like a normal residual type of a thing, as we saw in the GPT, for instance. In this example, maybe in some papers it has been shown that adding is better. Notice in the find that's what they're using. They're adding instead of concatenating. All right. So, but yeah, this is basically the UNet is exactly as we discussed. So now I'm going to talk about the loss function, which is really what I wanted to stress. So that's the loss function right there. At the end of the day is a MSE, actually, mean squared error, right? So it's a type of an MSE. It just took me a while to understand this. In particular, what the hilarious plus here threw me off for a while. All right, so, but anyway, so I created a little diagram, a very sophisticated diagram of how Stable Diffusion works. All right, and I'm gonna start with this, and then we're just gonna go over the notes. Okay, so basically, Stable Diffusion uses the UNet architecture, which we have discussed already. Right, remember that it's basically something that sometimes is called a variational autoencoder or an autoencoder. The idea being that input comes in and it gets downsampled to a latent state, and then from that, from a smaller state, and then from there it gets upsampled, right? So this was discussed already, and the properties of the UNet itself. But so what is going on, right? So we know that, and we've discussed already that the idea with Stable Diffusion is we have an image and we add noise to it until we end up with a noisy image. And then we reverse from the noisy image back to image, right? So that's something that we discussed last Monday. The forward does not use a neural network. It is actually something called a schedule. It's almost like a deterministic thing, and just noise is being added in the forward. So where you need a neural network is in the reverse. All right. So this UNet basically that we're creating here. Okay. So that's basically the idea. So the goal of essentially the basic idea of the Stable Diffusion model is that you give it a noisy image input. So for instance, a 7 with some noise. Notice that I put in the dimensions here, 28 by 28. This is something that we saw last time we met. I printed the shapes, and what was coming out of the model was not a number, right? It was a grid also, right? So what was that grid about? So the way that, a way that you can think about it is the neural network is going to receive this image. It's a 7, for instance, 28 by 28, and it's noisy, right? This is the noisy. And believe it or not, what it's trying to predict is another grid that is 28 by 28 in dimension, but that represents the noise. So it's actually from that image trying to predict its noise. Do you guys see that? Instead of, for instance, you would think intuitively, when we have denoising filters, etc., you give it an image like that, and what you would want is the 7 without any noise. But that's not how this works. Instead, is like the counterintuitive idea of the model predicts the noise in that image. Do you guys understand? So like I have a 7 with noise, and now basically this noise in a perfect world should be exactly this noise, but without the actual image. Okay, so that is the neural network, and that's what it's doing. We will print out the dimensions later on the MNIST, and we'll be able to see that. So then how do you train this model? So if you notice, and one thing I do want to stress, I even wrote it down here, although I drew this at the image level just to kind of make it clear, right? I want to stress that processing happens in a latent image and not in the actual image. So you have to use your imagination and think, okay, this image actually goes through compression, right? This is 28 by 28, so maybe it gets compressed to 14 by 14. That's a latent image, so it's not the original one. And that's just for further processing, okay? So that's the basic thing that you should understand. So this is happening, but at the latent level to be more efficient, and it works. So then once you have that, what really is the loss function? So the loss function is actually this predicted, right? So this is the predicted. So think of any neural network, right? You give it an input and it gives you an output. So the output of the neural network here is a grid that is, well, it's going to be a batch by channels by 28 by 28. I've simplified it intuitively just to be the, like an image. So it predicts, let's say, this grid of 28 by 28. So we're going to call this the predicted noise grid. I even used the word just so it's clear. So notice here, then the loss function is pred noise grid 28 by 28. It would be essentially this one, okay? And then what do? You basically calculate the difference between this one and the real noise grid. So there's going to be a point where you have an image and you create the noise, and you noise it. You see that? So you have the normal image and then a grid that is the same size of the noise, and boom, you have a noised image. Okay, but that noise is the real noise. And then the model is going to, given this image, try to predict noise, the noise in the grid. And then basically the objective is to take the difference between the two. So as you can see, it's a classic MSE, except that is 28 by 28 instead of how we've been doing things where we usually do like temperature and we predicted 72 and it was 75 and we take the difference of that and square it. Keep in mind here, it's the difference between the grids. So in this simplified example, grid 28 by 28 predicted, grid 28 by 28 real. But both of them represent the noise. And that's basically the objective of the loss function. And we will see that in the Jupyter notebook. So I printed out all the shapes and the values just so that we can arrive at the thing. If you notice, MSE would have a, usually predicted minus real squared, something like that. The loss actually in the code has a plus in there. And we're going to see why that is in a while. That's actually something that took me a long time to figure out. So then the substract of this is, so the idea is now, if you can think about it, you have the noisy training image, right? And you're learning, the intuition is the neural network is learning to predict the noise in that image. Why? Because then you have an image and its noise, and then you take out, you subtract, right? So the actual image with the noise minus the predicted noise gives you a clear image. You see that? And that's kind of the intuition, so you can start to produce things. And that's how it works. It's actually straightforward, right? And so we will look at that. So I wanted to start with this little chart just to kind of give you an idea of how it works. And, I like, as you have seen all semester, I live by the shapes of the tensors, right? That's always how I understand things. And so that's the idea. So I added some notes here. So basically, as I said today, we're kind of just focusing on loss functions, pretty much as we understood a lot of the other parts already. So basically, the loss function here is essentially the difference between, so I added some notes, the predicted noise of size batch by channel by 28 by 28, right? So that we'll see that in the code, and the real noise of size batch by channel by 28 by 28. All right, so that's really what the loss function is trying to do, okay? So that's actually pretty straightforward, right? Now, here's the key thing, right? The key thing that, we'll see. The values in pred noise and in real noise in the grids, right? So in these, I'm talking about the values in here, right? In the predicted and the real. So the values in pred noise and real noise grids are in the range from -1 to +1. All right, so they're normalized from the 0 to 255 that you would expect in a pixel there. So because of that, some values are negative, some values are positive. And that's why the plus was in there, because it's really that, you just like take the difference between them, where some of them have a negative, some of them have a positive. Do you guys see that? And so, it works out still as a difference. So therefore, the loss can be pred noise plus real noise squared, given that these are grids with, minuses and pluses inside. So that of the 28 by 28 on the pixel level, we will be taking the differences. Okay, so that's the idea. So this Jupyter prints values of loss parameters to understand the loss equation. So I'll go once I finish going over these notes. We will go over this Jupyter notebook. I encourage you to run this on your own and print all the values. But I've already done it, and so I'll show you the basic logic. So this just goes over the loss function, right? So it's not the entire code. I just really wanted to focus on that key, as that is a key aspect. Does that make sense? All right, so we'll go over that. The approach involves training a neural network basically to denoise samples using the denoising objective, expressing the same idea in a way closer to the actual implementation. And this is actually what the loss looks like in the code. And it looks, not tractable, but it's actually straightforward. So this is the predicted image, the predicted noise image, and this is the real noise image. Does that make sense? So then basically you have the original image and you add the noise to it, but where the noise is, if you notice, this is the initial noise grid. So when you're going to noise the image, imagine you have a 28 by 28, you just create a random noise grid, right? And that's going to be the real one. So that's this one and also this one. And then you're just going to multiply that times this function, which is dependent on time. And that's what actually modifies the noise to be corresponding to time 2, time 5, time 20. A simple way of thinking about it is at time 2, there's a lot of noise. At time 999, there's very little in the noise image, right? So that's basically what is happening. So if you think about it, the original image plus the noise that depends on time compared to the actual noise over there. And this is just the difference between the two. This is the L2 norm, which is a type of, distance metric, and it's squared basically. So I wanted to give you this formulation because we'll see this in the code. So we want to trace it back, okay? But that's the objective function. So epsilon here, which is this value, is the noise grid. It's important to understand the concept that our aim is to predict the amount of noise added to each part of our sample effectively at every time step t of the diffusion process. So this thing that modifies E is the function dependent on time. So, and that's, like a deterministic kind of a thing, okay? That's basically all that's doing. So think of it as noise times something, but the values there depend on T, right? So, a lot of noise versus little noise. And that's it. And it's not a linear denoising. It can be like other distributions. Okay? That's the key of it. And we'll see it in the code, and it should become more straightforward as we start printing the values. So S represents basically the unit. So you can see S is this function that encapsulates the data, right? So if you give it the noise image, and you're going to try to predict, as I said, just the noise of it. Okay, that's what it's doing. So the unit which predicts the noise grid, this theta is a function of time, noise at time t, basically, to modify the noise. Learning the S function is like transforming random noise into something meaningful. Yeah, and then this loss function figures out how wrong our model is while training, which is what the loss function does. Okay. Right. So, and it checks the model's prediction and compares it to reality, based, I've mentioned already. All right. So those are the notes, right? And as I said, I'll repeat the key things to remember, right? You give it the noised image. You give it the noised image. How do you do that? X0 is an image without noise. And then you add to it E times this sigma T, and that adds the noise. That's an input to S, this S over here, which is the unit. And what is that going to return? Just the noise grid, right? And then you compare that noise grid to the real grid and take the difference. That's it. That's the magic of Stable Diffusion. It's actually pretty simple. Any questions? All right. So, yeah, go ahead, please. So it's trying not to, I mean, it works, right? So one of the things that it says is that we don't process in the real image. We make a compression of it. So once you would lose information, like when you get here, but that is why units take what came out of here and add it over here. You're going to get that back. Exactly. So it's like you're compressing into it's capturing the essence of it, right? But then from the essence of it, you may not be able to recover the full image. You need kind of like the original ones to come in. And that's what the unit does. So imagine that this image creates a smaller grid here, right? But it's the same as in size. It would be the same as on this side. They're the same. So then imagine this one is 14 by 14. So then over here, it's also 14 by 14. So you can pass that to here, even though it's upsampling from this, you're still passing this to that. And that's exactly the definition of a unit. And the operation to put these two together is either concatenation or addition. So imagine if you have 28 by 28 and 28 by 28, you just concatenate it and it's a double, or you add it, which is 28 by 28, but they have the same dimensions, so they can be added. Do you see that? So that's the definition of the unit. It's a good question. So that seems to recover, and we saw it. It's in the code. Like literally, if you look at the transformer, sorry, not the unit in our code has. I think I showed that last week, where we could see the concat, and in the unit res, you could see that it wasn't concat, it was add instead. And I can point that out again if you need it. Got it? All right, so that's the overall idea, right? So it's actually simple. And then let's look at the code, because this is what I liked, as I said, when I'm looking at an algorithm, I start printing the shapes every step of the way just to kind of see what's going on. And that usually provides a lot of clarity. So let's go ahead and take a look. So the notebook that I added for that is this one, Loss Small Stable Diffusion, which is the same as this one here. So we can trace through the neural network and just see. So my goal here, is we need to focus on two things. So we're going to focus right. So, oh yeah. So to kind of to follow up on the question, this is what I was talking about. If you see torch cat, right? Basically, it's taking H3, which is this one over here, the grid at that, at that part of the network with those dimensions, and it's being used again over here and added to this H, which is so basically the decoding is coming from the tiny latent being upsample, right? But you add the H3, which is coming from over here, right? So you're getting that back. And so here you can see H2 is being added, H1. So like it was going down, now it's going up, and you're just adding that back. So that was your question. All right, so the thing to look at here is the loss Fn, which is this one, right? So the loss Fn is this function. If you notice, I did a lot of prints just so that we can see all the parameters in the loss function and the dimensions, okay? So we had done already the image, and that's still there. So all these prints, I'm going to go over them. But basically, I want to stress this part here, okay? That is the loss function, the thing that I just talked about. So I'll reopen that actually. Oops, what is that? No. All right, so GitHub, latent diffusion, stable diffusion. And if you notice, this loss function that I wrote like that, okay, we're gonna look at it in the code. Okay, so simply look at the fact that you have S, this is going to be a score, and then you have the image, which is going to be perturbed by the noise and this sigma function. And then you have the actual noise, the real noise grid here, right? So you have these values. So notice, let's break it down to just this whole thing. Imagine it's a whole thing, A, plus this other thing, right? Squared. Do you guys see that? So let's just keep it simple like that. So we can take a look at our code over here, and we can see we have pretty much the same thing. This whole thing, A, right? Plus this other thing squared. Does that make sense? So that's basically what I was talking about. So we're squaring it. This is basically the noise. Okay, this is going to be the noise, which means to corroborate this, this should be something like batch size by 1 by 28 by 28, because it's the grid of the real noise. Okay, so we need to, if you're thinking, okay, I think that's what this is, well, when you print the shapes, it should be that. This one over here, if you notice, right, is just this function score, right, times this standard here, this standard value, okay? So if we look closer, score is over here. And score basically is the unit model that we've talked about. What does it take? It takes perturbed X, which means it takes the image after it's been noised, right? It goes through the model, and then this thing is a grid, is actually the model predicting, okay, that's the noise grid of this input that I just received. So in essence, score here is the predicted noise in the image compared to the real noise in the image, and then just multiplied by some factor, which is those factors of time, basically, and the noise itself. So that's done separately, and we'll see that this calculation in a minute. Does that make sense, guys? So that's the loss function. So you can see it's squared, and then don't worry about this mean and sum. You'll get it in a second what that is. The key thing to understand is you are comparing the noise grid C, the real noise grid, to the predicted noise grid. Okay? And you're squaring it. And as I said, the plus is because, as I explained, because of the minus and the pluses in the value. So remember, this is grid to grid. So let's take a look at, well, we know what score does, right? So we know what score does. Standard here, if we will see that it effectively takes the same dimensions, the same rank of 4 as score, basically. So we can see here, as we come into this, we can see that we create a random t, which is basically the time, okay, that you're going to have in the process. All right, so that's the time. We'll print this. And then notice that this standard that we get is actually the thing that determines the noising based on time. So we have this function, and this function depends on random t, where random t, think of it as being at time 20, at time 100, at time 950, etc. So that function is the thing that's dependent on time. And then this one over here is the noise, z. So notice that it is basically the same image, and we just create a torch tensor that is random, and it's like x in terms of dimensions. Does that make sense? So we create the noise image here, z, for everything, the real noise. And then here we have, based on time, how we're going to modify it, okay? Based on time. So this standard and this C, right? And you can see it here. So C, which is the noise, multiplied by this time-dependent matrix or tensor, and then that is added to the original image, and you have noised the image or perturbed it. So if you look at this, this is very similar, as I said, to this idea. So this x0, you can think of it as the original image, x, and then you can think of E as C, the actual noise, and then you can think of this sigma t as this standard here, because we've established that this standard over here depends on marginal, which depends on random t. And these are fixed things, right? So not dependent on the neural network. That's it. That's the basic idea of it. All right. And so we start, if you notice in the code, in the loss function, get the t, fit the t into the function to get the standard dependent on time. Now initialize something random noise of the same shape as the image. Perform the operation. I printed these over here, the images, but here is where we perturb the input data with generated noise. So now we have that image. Perturbed x then goes into the model, as you can see here, with the time t. And then basically the model will produce the predicted noise for that image. So image original with noise, and the neural network tries to predict its noise. And then, you would try to remove it to arrive at the original one. So this score then, as I said, you come to the function here. So it's going to be that grid normalized by that, and then you take out, and you take the difference between the two and square it. So as I said, in MSC, you usually have this minus something, predicted minus real squared, right? But here you have this plus. So let's take a look at why that's okay. So the best way to do that is to print out all the shapes, okay? So now I'm gonna, in this Jupyter, I have a way of printing out all the shapes. So I already ran this code. I encourage you guys to run this, on your own. But you can see here, this part here is where I'm going to print all the values. I just did it for one epoch, basically, for one iteration. So we had done this already, right? This intuition that I give you the original image. And what do? We add noise to it. So this is this same image noised. And that goes into the neural network. The neural network should predict just this noise without the one. And that's the objective. So let's take a look then. Any questions, guys? So let's take a look now at the shapes of this. So we have the images are 2048 by 1 by 28 by 28, right? So batch, that means what? There's 2048 images in there. They're black and white, and they're 28 by 28, right? So those are your MNIST data. Because this is conditional, this is the labels. Basically, each image has a label. Random T, right, is going to be a value for every single one of the images, the time T that you're going to pick at random, right? To noise. Standard is going to be something similar, dependent on that random T, right? So we go back. We can see that, as I said, standard is the value given the random T value, right? So that the amount of noising. So we have the noise, and then how much we're going to modify that based on the time T, okay? All right, so that's basically that one. So one value for each one. The X is, so the X, as I said, is the images themselves. Z, if you notice, this is important because what is C? The noise, right? C is the noise. There it is. So C is nothing more than a random tensor of the same exact dimensions as the images tensor, and it's just the noise. So that's C. It should have the exact same dimensions as the images, because we need one for every image. So that's, I believe, so I was there. So this one, right? Z. If you notice, it's the same as the images over here. 248 by 1 by 28 by 28. Then here we take the original image, we add the noise to it, the perturbed image. Now we're going to look at the values, the loss parameters, right? So I just want to, finalize this by showing the shapes that are going in. So if you notice, score, right? Score is the thing that comes out of the neural network of the unit, right? And what is it exactly? If you notice, it is 248 by 1 by 28 by 28. That should be very clear, right? That it's essentially this one over here. Can you guys? Yeah, this one over here, right? I've just simplified it. But it's predicting a grid of just the noise. So that's why it's 28 by 28 by that. Standard gets expanded so that it can process the image. So standard, what is the shape of standard after expansion? You can see is basically that. So it has the same dimensions as this one, so you can perform the operation on it. C is the noise, basically. And so now you have these two things. What I want to stress here is you have this one, right? And you have this one. C and score, let's say. And you're taking the difference between the two, okay? Just like in classical MSE, you're predicting the temperature, 33, the real temperature was 28. Take the difference, square it, learn, right? So that's the same idea. We take the predicted noise and the real noise. Basically, essentially, two tensors of the same dimension, and we need to take the difference. And there isn't a minus, instead there's a plus, as I said, but that's why I printed the values. So if you notice, I printed the values of score, right? So score is this one, right? The predicted noise. But if we look at the values, we got they're no longer 0 to 255. They've been normalized. So you can see some are positive, some are negative, etc. You see that? So whether you do a plus or a minus, you're able to try to minimize that difference. Okay. So that's that one for the score. And so for the Z, it should be something very similar, right? And so we're going to print that out as well. And if you look, when you print out Z, which is this one, the vowels of C, you can see negative, positive. So you're effectively able to take the difference. Does that make sense, guys? And that's, you know, the optimization function for Stable Diffusion. That's the whole thing. If you notice, when you normalize it with standard deviation, you get the exact same thing. And that's also positive and negative. And that's the end of it. Now, to wrap up, so you would get, let's just, you know, this is going to result in a 248 by 1 by 28 by 28, right? But let's just simplify that and focus on one grid, one of the two 28 ones. So we have 28 on the pred, 28 on the real. Take the difference of them. Now we have one that is 28 by 28, right? And then you can just sum them and average them, right? And that gives you the average loss for all of them. And that's basically what happens here. That's why the loss function ends up being just one number. But if you look in the code, in the loss FN here, right, the loss FN, if you notice, there's a mean and a sum, and that's just a classic thing. Like whenever we've had a batch of differences, we would just take the mean of it or something. That's it. So hopefully that made sense. That is the loss function of Stable Diffusion, you know, and key to understanding is, you know, the fact that you're creating these grids, and then the predicted noise from this image is compared to the real noise of this image. All right. So that kind of concludes Stable Diffusion and what I wanted to cover of how the model learns, right? Which was the last little bit that was left. All right, so I'm trying to think here. The next thing, so I'm gonna stop this video and I'm gonna start a new one.